Have you ever wondered why your bread tastes so good? Have you wondered why that cake you're eating is so soft and delicious? Or why those cookies that you're eating are so crunchy and crumbly? It all comes down to one basic ingredient: wheat flour. But it's not always that simple. Producing a quality flour product from a truckload of grain requires many steps. One very important aspect of food production is quality control. Samples of the product are tested at various stages to ensure it adheres to the required specifications. One important component of wheat flour is the protein content. The protein in wheat flour is a combination of the monomeric and polymeric prolamins, gliadin and glutenin, which join together to form gluten. The gluten level determines the hardness or softness of the flour. A hard flour is higher in protein and it's stronger and more elastic. Soft flour is lower in protein, is less elastic and more crumbly. There are currently two different techniques available to determine the protein content of wheat. This presentation will focus on the comparison of near-infrared spectrometry and the LECO combustion analysis for nitrogen content. Near-infrared spectroscopy, or NIR. Spectroscopy dates back to 1666 when Isaac Newton first passed sunlight through a prism to exhibit a colour range. It then became the science of studying the interaction of various types of radiation with matter. The electromagnetic spectrum was born and this radiation could now be measured. Electromagnetic radiation contains a certain amount of energy. When it's absorbed or emitted, a permanent transfer of energy occurs. This radiant energy can be measured in wavelengths for different regions of the spectrum. Light and colour are visible to the naked eye at between 400 to 700 nanometers. The infrared region of thermal radiation is invisible to the naked eye and measured in nanometers, from 700 nanometers onwards up to 1 millimeter. It was first discovered by the astronomer William Herschel in 1800 and is still used today in optical spectroscopy. So what does an NIR spectrometer actually do? It measures the overtones and the combination tones of molecular stretch vibrations involving hydrogen bonds between carbon and hydrogen, oxygen and hydrogen, nitrogen and hydrogen, sulfur and hydrogen. And how does it do this? Well, a beam of light strikes a diffraction grating, separating the light into its component wavelength. The light then interacts with the sample and the detector measures its transmittance and absorbance. The science has evolved over the years and today there are many different models of NIR spectrometers. Here's a demonstration of the Unity Scientific Spectrostar Analyzer in action. It uses monochromator technology which selects a narrow band of wavelengths. NIR spectroscopy is based on the absorption of electromagnetic radiation at wavelengths between 780 and 2,500 nanometers. This increases accuracy when analysing for a known constituent such as protein. Once the flour sample has been placed into the analyzer, the infrared light radiation is passed into the sample and the transmittance is measured. This is how much light passes completely through the sample and strikes the detector. The absorbance is a measurement of how much light is absorbed by the sample. The transmittance and absorbance of the infrared light radiation produces energy within the molecules. As this energy increases, the molecule is promoted to an excited state which emits vibrations. The overtones of the stretch vibrations between the carbon, nitrogen, hydrogen and oxygen bonds in protein molecules are measured in wavelengths. The wavelengths and the levels of absorbance can then determine the concentration of protein in the sample. NIR spectrometers are useful for the quantitative analysis of known compounds. They can analyse many biological systems, have a short measuring time and give results within seconds. There is little or no sample prep required. Several analytical results can be predicted from the same data such as protein moisture and ash. It's a non-destructive measurement method and bulk samples can be used. The analyzer can also be used on the production floor. This saves time and money as the quality of the product can be monitored in real time. Some disadvantages of the NIR analyzers are that they cannot predict unknown compounds and they're not as precise as the LECO combustion method. When bulk samples are used, there also may be contamination and interference from other compounds, giving an inaccurate reading. There's also the initial cost of the machine, which can be around $10,000 to $20,000, and the cost of downtime when repair and maintenance are required. The Dumas combustion method of protein analysis was first developed in the 18th century and is used to determine the nitrogen content in food samples. LECO is a worldwide company that produces these analyzers. The LECO Dumas combustion analyzer combusts a sample of flour in a furnace at 1000 degrees Celsius in the presence of oxygen. Nitrogen gas is produced from this combustion and reduction reaction. The total content of nitrogen gas is measured using a thermal conductivity detector. The protein content is estimated based on the amount of nitrogen gas using nitrogen protein conversion factors. LECO is a commonly used method for the quantitative analysis of protein in food samples. It's a fast and cheap method with an analysis time of 3 minutes per sample, costing between 37 and 50 cents. So it's ideal for industrial applications. It doesn't require toxic chemicals as a catalyst like other methods do, such as the Kaldal method. You get accurate results and it's suitable for reporting on a certificate of analysis. This method requires an intensive training program costing time and money. The initial cost of the machine can be up to $100,000, which is a large outlay. It can't be used on the production floor for real-time monitoring as it has to be used in a laboratory setting. It requires regular maintenance and ordering of gas cylinders, which must be stored according to OC health and safety regulations. It also only calculates total nitrogen content, so different types of protein cannot be determined. Non-protein nitrogen cannot be distinguished from protein nitrogen, so this could affect the total nitrogen content result as well. This method is susceptible to adulteration, which may include the addition of non-authentic substances or removal of authentic substances without the knowledge of the purchaser. This means tests are able to be fooled by adding cheap compounds containing nitrogen, which may result in damage to consumers and legal action. So which method is better? Both have advantages and disadvantages, but both methods are acceptable for use in quantitative analysis of protein in wheat flour. The determining factor for your choice of method in your laboratory would come down to cost, space, reason for use, legal requirements for testing your product, amount of staff, cost of training, and what level of accuracy do you require. And thank you for watching.